So any other questions?
Number 4 on 324, so page 126.
So they got weights. One is of men, one is of women. Can you tell me the median? So this is page 126, number 4. Can anybody tell me the median weights from those two?
169.95 and 135.8.
Yeah, so one median is 169, and the other median is 135. Even just from that, which one's men, which one's women? These are weights of people.
Well, see, that's what I was confused, because it says it's a random sampling of them, so either one could be, technically.
Good point.
It's a random 5 men and 5 women.
Gotcha. But what would you expect to be true?
The men would be heavier. But
Yeah, you would expect the men to be heavier.
Well, you would expect the women to be lighter,
And you got one outlier. You always have the possibility of an outlier, right? You expect men to be taller, but then you have some men not very tall at all. You expect women to be shorter, but then you have some women that are very tall. I mean, so there are outliers, it's fine. The real gist of this is, where are the majority of these people? And look at the boxes. Go beyond just the medians. Most of the people on the lower one are from 116.9 to 162. And not most, but how much exactly? What percentage is in that box? 50% in that box, right? Because it's between 75 and 25, 50. 50% in there. 50% of the top box is between 152 and 190. Right? I'm glad my weight's not way far off one end. That would suck. I'm somewhere in there. You guys semi with me so far? So I mean, really all I'm asking is, which box plot represents women? They really should say, like you're saying, they really should say, which box plot more likely represents women? And which one more likely represents men? How do you know? Which one depicts weights with more variation? The top or the bottom? Which one has more variation in it? Yeah, the bottom one, for 2 reasons. One is that little middle box is a little longer, and really the main key is the whiskers go out further, right? So there certainly is more variation. There are more data points further away from the middle. Okay, sort of. All right. I'm depressing more students this semester than ever. I'm not sure what it is. I'm a math teacher. I'm used to it to a point. It's just more than normal. Okay, that didn't even, geez. I was hoping that would bring a smile and everything. I know you're trying to be funny. I appreciate it. That's the extent. All right. Any other questions from homework? Okay. All right. So last time we got a little bit into probability, and I'm just going to do some, and I already kind of warned you about this. We're going to just kind of go through an example, and I think I'm going to make it easier on me, because I think a few of you guys said you don't really know cards too well. Cards, you just make it so easy. I'm going to throw up there. I'm going to throw up here a set of cards so you can kind of see them. But let's kind of, you guys help me characterize cards. How many cards are there total? 52. I had an older sister, so I knew all too well how many. It would be random 52 card pickup games. Pick them up. Whoa. How many suits are there? 4 suits. And what are those suits? Hearts. Diamonds. Sounds like we're eating Lucky Charms. Spades. Clubs. I like the clovers. That's good. These are red. These are black. How many red cards total then? 26 red. 26 black. How many of each suit? 13. There's 4 suits in the 52 goes 13. How are we doing so far? Does this sound familiar? And then let's treat ace low for right now. It goes ace, 2, 3, up to 10, and then of course Jack, Queen, King. These are also known as face cards. All right, and that's basically all you need to know for right now. I'm not going to launch into, and here's how to play poker and make money. Obviously, if I could do that, I probably would be doing that. I don't have a poker face at all, though. I'd be that guy that goes. Buy some really big ass sunglasses cover my whole face. All right, so let me ask you a couple get our feet wet kind of questions. If I pick one card, and of course that makes it sound like later we'll be picking more than one, yes. What's the probability I get red 8? So what's closed on the bottom definitely? 52. There's 52 total possibilities. I'm picking a card. It could be anything out of 52. How many match what I'm looking for? 2. Because there's a diamond, an 8 of diamonds, and an 8 of hearts. You guys with me? So there's 2 cards that match what I'm looking for out of 52 cards. And of course, if you want to know, that reduces to 1 out of 26. You can make that into a decimal, a percentage, but definitely show me the fraction work. If you just have a decimal come at me out of nowhere, I have no idea where that came from. If you get it wrong, you lose most of the points. I don't know. Show me the fraction, I can tell how close you were, what your thought process was. What about the probability I get king? 4 out of 52. And what does that reduce to? Yeah, and I think we talked about that last time, right? So in case anybody needs visual assistance, let's see what I can find real quick. Yeah, there we go. All right, so obviously no, that's funny. No foot cards are in here. All right, so if you want to play with your foot deck, you can. That's I like that. Those are mostly jokers. So you guys said there's 52 cards. 4 of them are kings. That reduces to 1/13. You can make that into a decimal or a percent if you want to. Because we're human. You tell me 1 out of 26. Well, what is 1 divided by 26? Did somebody do that? Can somebody do that?
It's 4%.
About 4%? Yeah, 1/25 is 4%, so 1/26 is just under that, 3 point something, yeah. So if you tell somebody you got a 4% chance, around a 4% chance of picking a red 8, now as humans we go, okay, I'm not going to put a lot of money on that. But if you tell me 1 out of 26, I don't really have a good feel for that, right? Is that true? If you do, cool. Most of us operate better with percentages, but show me this work here, so I know where you're coming from. What's the probability I pick a number less than 5? Treating aces low. Aces are 1.
20 out of 52.
20? How'd you get that?
There's 5 cards less than 5 in each suit.
Good. So there's 5 cards that match what I'm looking for in each suit, and there are 4 suits, so there's 20 cards that match what I'm looking for. You guys still with me?
Yeah.
So 1, 2, ace, 2, 3, 4, 5.
So we're just counting
Oh yeah,
each.
less than, you're right. I'm thinking about, and I didn't even write it correctly. Strictly less than 5 would be 16. And if I said less, at most 5, that'd be 20. Cool. So I mean, the basic idea of probability, and to tell you honestly, I'm almost sure you're not going to believe me, but I'm going to keep trying to come back and tell you, no, it didn't change. It never changes. The idea of probability never changes. So let's take the next step up. If I pick one card, what's the probability I pick an 8 or face card.
Or 52.
Yes, how many face cards were there in each suit? There was the Jack, Queen, King. So there's 3 in each suit, so there's 12 total. You guys with me? So there's 12 face cards.
Plus 4 8s.
And 4 8s. So the top number, the bottom number, of course, is going to be 52 for any of these card questions, right? I'm not going to be evil and throw jokers in there. There's 52. The top number is always the total number matching what you're looking for. That or gives me more chances, doesn't it? You'll win $5,000 if you pick the right number. Or if you pick 2 numbers that add up to the right number. Or, and now I'm getting more and more ways to win here, right? Okay, you guys are, okay. You guys would kick my ass in poker. You're bluffing. And then you can reduce that. Cool. And of course, not surprisingly, this reduces to 4/13. For every 13 cards for every suit, there are 3 face cards and 1 8. So very often the ratio you get when you reduce actually tells you something physical about the problem. Okay. How are we doing so far? Yes, sir.
What do you mean when it doesn't change?
The bottom, the
No,
52.
when probability doesn't change, why would it change?
What did I just say?
Well, before you went into number 5, you're saying we're not going to believe you, but probability doesn't change.
No. The basic idea of probability doesn't change.
Why would it change?
And when we get to the more complicated stuff, you'll start questioning my sanity. Yeah. But it's always the total number of things that could be on the bottom and the total number of things that match what you're looking for on the top. Right? It's always that. There are formulas that make it look like it is in that, but those formulas start from that idea. Okay, so we're getting there. We're building. What about this? Here's a little bit of a, I'll tell you right up front, this is a trick question. A jack or a club. Let's think about it. Don't say anything out loud. Based on what we just did. I told you it's a trick question, but not a major one. So just do what your heart says to do, and we'll see. 16. Don't say anything out loud, I thought I said. Of course, a good place to start is the bottom is going to be 52, because it could be any of the cards. How many are jacks?
4.
How many are clubs?
13.
But what's wrong with that? Yeah, there's one card I've counted twice. Nobody should get to be counted twice, right? You with me? If I said all the men stand up, and then I said, and I counted everything, I said all the Democrats stand up, and I counted them and say, oh, add them up to how many Democrats? No, crazy person. Some are mixed, and some men aren't Democrat. There's a lot of things going on there. Here, I've got to adjust this number. You could be smart about it and not double count in the first place. You could say 4 jacks and then 12 other clubs besides the jack of clubs already counted. You with me? Or you can right here say 4 jacks, 13 clubs minus the one that's both. Right? What have we done so far? You guys, I can't read you at all. You're scary. 16 out of 52 again. Okay. Maybe. So here's the formal definition then of or and, well, just or for right now. We haven't done it yet. Or officially, the probability of event A or event B is officially, you add them, but then you have to subtract off what?
1.
Not always 1, is it? Why was it 1 here? Because there was just one card that was both. So let me do another one off the heels of this. Probably I get a jack or a black card. Well, how many are jacks? 4. How many are black? 26. 26 plus 4, but I got to subtract off how many? 2, because I've already counted 2. So you got to be careful. It's not always the same number here. It's not always 1 or 2. It's always the number of things that are both or intersecting. I like it. Another name for that. So minus the probability of A and B. So for example, here we subtracted 1, because there's one card that is a jack and a club. Okay. So this is the official formula for OR. And I'll tell you this. Chapter 4, probability is important. It's a part of this class. To do the statistics for the rest of the semester, I will make a big point out of what's really important. OR basically means add. OR basically means add. Why do I say that word basically? Because you have to adjust it sometimes, right? Why didn't I subtract anything up here? Because there are no 8s that are also a face card. If there are, don't play with that dude. Right? Bring your own deck, something. All right. How does it work? So, let me ask you this. Let's say we're playing this game and you're going to put some money down, and I pick a card out of a deck of cards. And you put some money down on it being a king. You think it's a king. Right, so far so good? Okay. So what are your odds are? What are your chances? What's your probability that you're gonna win?
4%.
Gotta be careful now. It's higher than 4%. What is it? How do you build it up? We already did probability.
No,
4 out of 52.
8%.
Yeah, roughly 8% chance.
Does it work for blackjack too?
It works for anything. As long as you can identify what the situations are. Now, of course, blackjack is difficult because what have they started doing a lot more? They use like 8 decks, right? And they keep switching new ones in. So counting cards and all that stuff becomes not impossible, but crazy difficult, right? I like that. You're the guy in the back going, how can I use this? Which is not a bad way to be. I'm not making fun of you. It's good.
I tried to do that, it didn't work.
No, you gotta be careful. The other thing about this too, I think I was saying this the other day. Probabilities are exactly that. They're just probabilities. You've got to stick with it over the long run. If you know 60% of the time you should win, well, 40% of the time you're gonna lose. But if you stick with that plan over the long run, you're gonna come out ahead. You with me? So a lot of really good poker players, I see this all the time. They're out early sometimes. Bye. Right? There's 4th person leave. Well, gee, he won last year. What the hell? And they're fine with it. Not totally fine. They're upset, but still. They know that's going to happen. They stick with their plan. They know it works this percentage of the time. They know they're going to be out sometimes early, but most of the time they're going to make it to the money, and maybe even make it to the really, really big money. Right? Even if you don't watch poker, still that makes sense. Hopefully. Now, let's say we're playing this game. You put money on the king. I've got my card here, right? And I say, you can ask me one question about this. And then based on my answer, you can change your thing. Now, sometimes people, go ahead. What would be a good question to ask?
Okay.
And I don't blame you for asking this.
Is it a game?
Is it a king? Right? So, now, that obviously does make sense. It seems to be a really good question to ask, because if I say no, then you'll change your answer, right? But do you have any idea how likely anything else is? So the chances, if you say, is it a king, and I say no, what are the chances it's a king now? 0. I just said it wasn't a king, right? What's the chances that it's anything else? Let's see if you guys get this. If it's not a king, what's the chance that it's anything else? It'll be
100%.
like 48 out of 52. Not 100% chance it's something else, but any specific other card.
Would be 148, right?
Yeah, 48 out of 52, so 90, whatever percent. Yeah. A better question to ask. Let me kind of help us out. So one question I could ask is it a king? And I say, no. So then you're going to change your card, but you don't have any idea about what's it good to change to. You with me? So it helps you with your immediate problem, but it doesn't help you with your future, what the hell else should I guess? So a really good question to ask would be, well, actually, let's start with another bad question. And hopefully you guys see why this is bad. Is it a heart? Can you guys feel out why that's a crazy, not good question.
Because it doesn't even tell you if it's a king or not.
Doesn't know it's a king. If I say yes, it's a heart. It's still a 1 out of 13 chance it's a king, right? Because you guys with me? What's the problem now? I just gave it away, but what's the problem? It's a king now. Here's the trick. What goes on the bottom now? If I say yes, it's a heart.
13 goes in the bottom.
These are separate. You only get one question, right? So this didn't happen. This is some other universe. This is the question we ask. Is it a heart? What goes on the bottom? 13 hearts. Do I put 4 on the top? There's only one king that is a heart. So do you see, probability didn't change there. This is what's called, I really want you guys with me. This is what's called a conditional probability. The probability is this on the condition that I know it's a heart. Did the probability actually change? To be a king, it was 1 out of 13. And it still is 1 out of 13, right? So this is really fully the probability it's a king given that it's a heart. And that's still 1 out of 13. So I gave you more information. I said, yes, it is a heart. What does that normally do for probabilities? Automatically, the bottom becomes smaller. If I said, oh, that might be Nancy coming, well, it could be out of how many gross month students. I say, but I know it's a woman. Well, now it's divided by just the number of women. I've cut the denominator down a lot. You guys with me? Okay. So somebody have a better question? Yes?
Is it a face card?
I love it. I was worried I'd have to. No, I'm not saying you should have come up with it, because I didn't know. I was worried I'd have to kind of lead it along too far. But a decent question would be, is it a face card? If I say yes, if that's the question you ask and I say yes, what's probably it's a king now, given that you know it's a face card?
4 out of 12.
I love it. There's 12 face cards, and out of those 12 face cards there are 4 kings. So what's the chances that you've won if you leave?
1/3.
1/3 chance. Much better chances than there were before, right? Before it was 1 out of 13, now it's 1/3. Before it was 8% chance, now it's 33% chance. I've quadrupled my chances, right? You guys semi with me? So the problem with this guy here, physically, I threw out 3/4 of the deck, didn't I? When I said it was a heart, yes, it's a heart. You throw out the clubs, the spades, and the diamonds. But each time you threw out 3/4 of the deck, but you also threw out 3/4 of the kings. So overall, it's the same damn, oh shit, same probability, right? Whereas here, I threw out, I kept 12 out of 52, that's a little over 1/4 of the deck. I didn't throw out any of my chances to win. I didn't throw out any of my kings. So now the probability is a lot higher. It's about 33%. Cool. Maybe. So see, the probability doesn't change. The idea doesn't change. This is what I was saying. The bottom is not 52. So sometimes people focus on, yeah, it's different. No, the bottom is always the total number of things it could be. If I know it's a face card, it could only be out of 12 things. Okay. All right. So let me show you the official formula for this. This is where people really start to question. Conditional probability. They just give you the symbol. This symbol is given. It's not A divided by B. Right? You can't divide king by face card. I don't know, I'd like to see you try. And this definitely doesn't say probably A divided by probability of B. There's no division in this. This is just a symbol that means given. Let's see if we can piece this together. Where did this 12 come from? Face card. So it seems like this guy goes on the bottom. The given goes on the bottom. So on the bottom goes the probability of the given. someone? You good? My third grade teacher, all she had to do was say, I'd say, I got hiccups. Let me hear it. They were gone. That was all it took. Anyway, why was this a 4 on the top, but the other one was a 1? Of course, I erased it, but the one when I said was it a heart? It was a 1 up top. Why was that a 1? King, given, heart. Why was that a 1? There's only one king that is also a heart. You with me? So what does it seem has to go on the top then? The top has to be the things that are what? So let's do another example before we figure out what that top is. So what's probably it's 7 given it's a black card. What goes on the bottom? 26, good. So the given goes on the bottom, 26. What goes on the top? 2, because those 2 cards are a 7. Where's the magic word? It's a 7 and, cool, black. Right, so that's why it's 2 up there. So on the top goes all the cards, all the things, it's not always cards, all the things that are A and B. King and heart, 7 and black. Because if only these things could happen, what's the only way an A could also happen? If it's also B. So if the only thing that could happen is a heart card, then the only way that a king could happen is if it is also a heart card. So it's got to be probably A and B. Now I want to point something out. You obviously will put these down on a formula sheet. I sure as all hell would if I were you. The problem is, did I need this formula? Did we need that formula when we did this? Because I have stuff that I can count. Probability formulas get in your way very often when you have stuff that you can count. I don't need the formulas then. I just need the idea. Bottom is the total things. The top is the number that match what I'm looking for. That's all I need. That's all that formula really says. But it looks a lot more complicated than that, right? And people start, when I give a problem like this, they start trying to force things in to work this thing. No, just count. The only time I really need this is if I don't give you something to count. If I say probably A is 0.7 and probably B is 0.6 and blah, 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 and you got to throw stuff into formulas, then you've got to use the formulas. But if you give me cards or something, you don't need it. How are we doing so far? All right, so just to catch up, we just done 4-3 and 4-5. See, I don't really agree with the ordering in here either. So this is 4-3. This is 4-5. So let's go back maybe and fill in 4-4. Before we do that, let me show you, and this will get some attention, let me show you how I would put a problem together. You would definitely have a problem like, well, let's do both ways. You'd have a problem like this. Well, I mean, I don't even want to do the problem yet until we get to 2. I haven't picked 2 cards yet, have I? That's where things get a little more interesting. You'll have a problem like this, though, for sure. Let me throw in there. I always like to put in there my ardent Paul supporters, right?
Should probably piss someone off.
Yeah. So let's just make up some numbers here. I know, I'm not picking mine anyway, don't worry. Trying to follow national trends here, sort of. Okay. So I'm going to give you problems in table form. So let me show you how to count. Now obviously, it's kind of silly. I can count, Jeff. What the hell's your problem? Let me show you how things like and things work in tables. They're really nice. Let me start off with, what do you think is a good first step when I start asking questions like, what's the probability I pick a man if I pick one person? what should I really do before I start attacking this kind of problem? What should I kind of do for myself? Yeah, I need to figure out how many total people there are so I can figure out what the denominator is, right? Out of how many. But it's also good to know each individual category, right? So I have these little boxes on the outside here. So this is 93, 89, 5. This is exciting, I know. 93. That's funny, Jeff. 92, 94. Okay. So that's 187, and just make sure it's 187 this way. Yes. Do not add these to these. I see that sometimes. Right? I mean, obviously I just didn't, so it's not a good idea. But if any of you are wondering why didn't I add those people in, because I already did, right? If I add this row, that's everybody. If I add that row, I can double check. So be real careful. Every now and again I get somebody that doubles what it really should be. So on the bottom of this goes what, of course? 187. I had 187 total people that I talked to. How many are men? Careful. 93 people did what? 93. Oh yeah, I'm sorry. I forgot. I'm like, I don't like double numbers because I can. So on a test, I'll be careful that I do it. So 93 people picked Obama. So don't say 93 because of this. Say 93 because of that. There are 93 men. You guys see how I read that? So I got to be careful about the assumptions I make. I'm very used to this kind of table. It's actually called a contingency table. Contingency, yes. So a lot of people tell me that would tell me this number for the men. They just look at this wrong. But I just read across. There's the men. There are 94 total women. 5 people want to vote for Paul. You guys see that? So cool. So you did 93 out of 187. So just under 50% there, I think. 49.7%. Nobody's doing it for me, so we'll
It's
number
49. It's 0.497.
497.
Yeah.
All right. Of course, you know this is my thing, so I better be on it. What's the probability? It's somebody who will vote for Romney. These are each different problems.
89 over.
Yeah, I'll never do that to you. I'll never kind of build and build and build. This is a separate problem.
89.
Yeah, 89 out of 187. What's the probability? It's a woman or somebody's going to vote for Ron Paul. Yeah, the thing you don't want to do is add these two numbers, right? Why not? Because 94 women, you've already counted those two, haven't you? So 94, you can be smart about it and go 94 plus the 3 I haven't counted yet, right? Or you can do 94 plus 5 minus the 2 that are both. And the really cool thing about both, and the really cool thing about somebody earlier saying intersection, and is very often considered an intersection, the intersection of women with Paul, that just sounds weird, women and Paul is 2. Right? So here I can do it several ways. I can do 94 plus 5 minus 2, and that'll be 97 out of 187. Or I can do 94 plus the 3 I haven't counted it. You can be smart about it. Not use the formula, just go screw you formula, I just count what I need. Right? Is everybody with me so far? This isn't crazy difficult, but for a lot of people it's new. Right? So I understand that. So of course I gotta ask you an and question. And questions are stupid easy with charts. It's man and we'll vote for Romney.
I have a question.
Oh yes.
On that last one, don't you have to add the 3 too?
I did.
Oh.
I really did, because that's 3 right there, right? So if I do 94 plus 5 minus the 2, that's the same as 94 plus 3 directly. So the other way to do this problem is 94 women plus 3 men who are going to vote for Paul that I haven't counted yet, right? So that's, but they end up in the same place. You with me?
Yeah, but I mean, like, don't you have, like, you'd say 94 minus the 2, because there's 2 women that are for Paul, right? And then wouldn't you have to add the 3?
Oh man,
and
be
then-
careful.
Okay.
You don't want to throw those poor 2 women out. They have to be counted once.
Yeah.
Just don't count them twice. So if I do 94 plus 5, how many have I double counted? 2. So that's when I have to subtract 2. But I'm glad you said that because I see that a lot too. Don't subtract anybody unless you actually have double counted them. Or you could be smart and say, here's 94 people, plus 3 more people that want to vote for Paul who I haven't counted yet. And then you don't have to subtract anything. You're just getting a total number that matched one or the other.
But you don't have to add the 3 and the 5 to it?
No, because there's not that many people here, right? There's 5 total people that want to vote for Paul, yeah. These are just summations, yeah. This isn't 5 extra people yet. Cool. Okay. And that's the kind of thing I have to be careful about because it's anytime you have a teacher teaching something, obviously they're very comfortable with it. But then I kind of forget what it is that's might be weird when you first see this kind of thing. So I got to be careful. So what would this be? How many are?
Like 3, man.
Wait, what's the question?
Probably it's a man, and they're gonna vote for Romney.
Oh, it's 48.
Yeah, 48. Why just 48? Because there's only 48 men who are gonna vote for Romney, right? That's the beautiful thing about and. And is really an intersection. This and this would be there. Just like one of the most hated things in algebra, finding the intersection of 2 lines. It's better. It's easier. Pop! Right? That's where they meet. There are 48 people that match both. And says you must be both. I don't know if I said this yet, but or, have I said this? Or is like the really nice bouncer. This is, I'm not going to let you in this club unless you're under 30, or you could be this, or so a bigger pool of people could come in, right? Under 30, or you could just look really good, or have a lot of money, give me some, or so there's a lot of ways to get in there. So there's a bigger pool of people that can get it. Now if he says you got to be under 30, and you got to have a lot of money, and I better like what you look like, and you better, then there's a smaller group of people. Sort of like when you go to look for a scholarship. Have you guys done that yet? And they say you have to be this, and this, and this, and very often it said last damn sentence. And you must be over half Native American. Shit. And you must have this. Damn, everything else was good except the last one. So that those ands cut the number of things down. The answer is always going to be smaller. So that's just 48. That's smaller than 100 whatever it would be if I did an or. So this is 48 out of what? Yeah, it's got to be 187. The only time the bottom changes is in what situation? Given. When I have a given, that's the only time the bottom can change. Now, we can reduce it. I'm not talking about that. Same at the first step. The only time it can't be 187 in this problem is if I give it a given like this. I just like the grammar of that. But we all know what I'm talking about. It's probably somebody's going to vote for Romney given that that person is a woman. So what do I know about this person? It's a woman. I know it's a woman. It's the probability that they're going to vote for Romney. I don't have a clue who they're going to vote for, but I know it's a woman. So how many people could it be?
94.
Could be 94 people. So out of those 94 people, how many are going to vote for Romney? And the really awesome thing is, that's your I can't do it this way really easy, but your whole universe is this here, right? So out of those 94 people, 41 are going to vote for Romney. There you go. And whatever that is. How you guys doing so far? So if I'm you online, give me a couple of those problems, Jeff. That's awesome. And there's definitely some of these in the homework. In a couple sections, there's these table problems. They are this easy.
Should we start with 4.3 for homework? Because 4.2 is more percent.
Oh, 4.2 you can do. That's just the basics, yeah, making those ratios. All right. What's the probability? Let me take a step back. Probably somebody's going to vote for Romney. Period. Yeah. Romney, 89 people out of 187. Now help me out. Those last two. Give me a estimated percentage there.
The first one is
146.
44%?
Yeah, and then this
146.
48%.
48?
47. Yeah, 47.5.
47.5? Okay. All right, is that cool? I mean, we can certainly do that. So the probability that somebody would vote for Romney is 47.5% out of this group of people I talked to. The probability that somebody would vote for Romney, given that they're a woman, is 44%. Would you say then that being a woman or a man affects the probability that somebody's going to vote for Romney?
Yes.
So would you say that those two events, being a woman and somebody who's going to vote for Romney, would you say those are dependent or independent? See if you guys can take that step. So let me take a step back. Obviously, being a woman had an effect on whether or not you're going to vote for Romney. And that's kind of a controversial issue right now in the news, right? Okay. So you guys with me? Would you say then that being a woman and voting for Romney are those events, would you call them dependent events? Do they depend on each other? Or independent events? Do they not give a shit about each other? Dependent. I mean, that's beautiful. It makes sense. It depends on each other. Romney by himself was this. Given woman, suddenly his chances go down to that. It changed. So to be dependent, they must actually care about each other, right? So we saw an example. These are definitely, so Romney, voting for Romney, and being a woman are dependent. The probability of Romney depends on whether you're a woman or not. Yes, sir.
So if it were independent, they would both be 47.5.
Exactly. To be independent then, the probabilities have to stay the same, which means the one event didn't care about the other event. Right? I'm not trying to say that these things have feelings and whatever, it just makes it easy to remember. So let me give you a real life example of this. I see somebody come in to the classroom. It's not my Nancy thing, but I see somebody come in the classroom, I'm like, is that a guy or a girl? What's the probability it's a guy or a girl? 50-50, I don't know. Shit. Then I say, oh, that person was riding a Harley motorcycle. Did the probability it's a man just change? Yes. Now, does that statement say anything about, well, no women wearing Harleys, because they do. It says more about the likelihood, right? That's what probabilities are about. So this dependent thing doesn't mean that if one happens, the other one's definitely going to happen. It just means if I see somebody getting off a Harley motorcycle, they are more likely to be a man. If I am talking to a woman, she is more likely to vote for Romney. I mean, not for Romney, sorry. Less likely to vote for Romney, right? You see that in there. Are no women going to vote for Romney? Of course, there are going to be women that vote for Romney. That's silly, right? But the probabilities change. That's what dependent is all about. Do the probabilities change? Okay. Let me show you. We got one last thing to do here. And that's actually one of the most important things. And that's that section 4.4. Let me get through this and then I'll try to give you, we'll see how much time we have, and we can do let you guys try a couple examples out yourselves. All right. So this is a very silly example. I will tell you that right at the start. But it's one way to kind of illustrate this. If I, let me see. Why do they do things, before I do my really silly one, why do they do things like this? I remember back in 87, I think it was 87. I lived in Florida. We used to go out and watch the shuttle take off. And that was the year, of course, the first explosion happened. And for some reason, they didn't have us go out. I was a major geek, so I was tremendously bummed out when I heard that it blew. But do you guys know why it blew? It was there were some O-rings that were supposed to keep things flowing in one direction, not the other. But they had frozen over, so they weren't operating correctly. Why do you think they had several of them in a row? They have several O-rings in a row. Why do people have several locks on their door? Why do people make backups of files? Why do we do these kind of things?
Margin for error?
Margin for error, I understand what you mean when you say that.
So that if one fails.
If one fails,
Yeah,
the other one.
so I increase the probability that I have one work. Why would somebody maybe have 2 alarm clocks on the day of the final? Increases the probability that they're going to actually wake up one time. You know, if the one doesn't work, the other one's, it's very, very unlikely that they both won't work. It's very, very unlikely that all these would fail unless there was one event that affected all of them, which was the freezing. You with me? So one of them could have failed just because it was a sucky little valve, or just had a little defect in it nobody noticed. But it has 2 other ones to back up. One person, they could crack one of my locks, but then all the other locks are different. So good luck, right? You guys with me? So it's the whole idea of the probability is going to go down as they put more and more things in place. So if the probability of an O-ring failure, this is not true, but we'll say it's 1%. You with me? If I had 2 O-rings in a row then, I don't know if I'm being too technical here, 2 of these things in a row, 2 locks on my door, 1% chance going to get somebody through the one lock. If I put 2 locks, I'm not going to add, that would suck. I'm not going to make it say they have a 2% chance now. Oh shit, so if I put 100 locks, like, whoop, it's like the locks undid each other somehow. You guys with me? So adding here doesn't make a damn bit of sense. 1% of the time, one of them would fail. 1% of those times, the other one would fail. What does of mean with percentages? What operation is of? So it's 1% of 1%. Do you guys get that? 1% of the time, one of them fails. 1% of those times when he failed, this one will fail also. You with me? So the and is really multiply. So we're sort of completing the whole picture here. We know what OR is. OR is basically
Add.
yes, thank you. OR is basically addition. And what's probably that one O-ring and the other one fails is multiplication. Because now what does this become? Yeah. Thank God, my probability just went way down. You with me? Somebody with me? That's what I expect to have happen. I don't want this to be an addition because then putting more things in place makes it easier for things to fail. That sucks. Don't back up your file, man. It's more likely to go. No, it doesn't make any sense. Okay. So let me show what this means when I'm picking like more than one card. And let's do this. You guys might realize how important this statement here is. With replacement. What does that mean? I have a deck of cards. I have a deck of cards. You pick a card, you put it back in, and then you pick again. So there's a chance that you might pick the same card.
Oh, I think.
Okay, semi with me? So the other situation, of course, would be without replacement. I pick a card, feed it to my little brother, and then we pick again. Right? Didn't like that one either. I actually did that. So pick 2 cards in replacement. What's the probability that I pick a king and then another king? So it's probably the first one is a king. How many times out of whatever does that happen? 4 to 52. So 4 to 52 times the first guy will be king. Of those times, what's the probability that the second guy will be a king also? Careful now. You're one step ahead of me. I put that card back in. Do any probabilities change? No. It's still out of 52, right? So times 4 to 52 again. Yes, sir.
So the replacement part means you just put it back.
Put it back in, so there, now imagine, I think somebody's a little ahead of me, if I did take one card out and throw it away before I picked another one, how many cards are there now? How many kings are there now? 3. So that's the next step. If I did this without replacement, that second probability would change. It has to adjust according to what happened, right? If I do it with replacement, the second dude doesn't give a shit. It's like, I still got the same chances. I've got all the kings in there I did before. This is 1 out of 169, which is whatever the hell that is. Reduce to 1/13, 1/13. And yeah. Obviously you don't have to do that. You can just, as long as you show me this, you can go ahead and plug that in your calculator and get that to a decimal, that's fine. As long as you see what work went into it. Let's probably pick, I could get, these get really evil easily. An ace, and then a club.
So you're not saying with replacement?
It's still with replacement. These are with replacement. Without replacement, I wouldn't even ask you this, because that would be remarkably, was that ace a club? Sometimes yes, sometimes no. So they have to cover for that. I wouldn't ask you that. Don't worry. So what about this one? What's probably the first card? What was probably getting an ace? 4 to 52. Put that card back in. What's probably now the next card is a club. Yeah, 13 out of 52 still. 11.
It's gonna be 1/4 times 1/13.
Yeah, 1/3 times, yeah, 1/4.
Times 1/13.
1
Or
1/13th, yeah.
times
Yeah, 1/13th, 1/4, yeah. So 1 out of 52 is what we're trying to say. And then whatever that is. Just under 2%. 4 times 13, yeah. Alright, maybe. So of course, without replacement, let me give you a different problem here. Let's probably get an 8, and then an ace. If I do this without replacement, let's probably get that first, that 8.
4 to 52.
4 to 52. Then I throw that away. So what changes?
4 to 52.
Yeah. The 52 becomes 51. How many aces are there? There's still 4 of them, because I just threw away an 8. Now some people will say, and maybe none of you are thinking this, so I always get possibly in trouble for this. Somebody's going to say, you write that like you know you got an 8. You threw an 8 away. No, these are all probabilities. 4 out of 52 times I will get an 8. If I get an 8, I'll throw it away and then I'll try to get an ace. This is a statement of possibility, right?
But you'd throw it away even if you didn't get an 8.
Yeah, even if I didn't get an 8, I throw it away. But this is out of those times that I actually get an 8 and then get an ace. So I don't know what actually happened. Right? This is all theoretical anyway.
If it picks an ace, it would be 3 out of 51.
Yeah, so like on this problem, let's probably get 2 kings. A king and then another king. What's probably that first guy's a king? 4 to 52. It's probably a second guy's a king.
3 out of 51.
I love it. So 1 less card, 1 less king. One 13, 117, 1 out of 221. And then whatever the hell that is. Okay. How we doing? So obviously it's very important if I say with or without replacement. So you guys try this one. Let me give you one that's not cards. Let me give you one that's a classic problem. And you all know this classic problem. Putting stuff into a bag, right? So you put 8 black, 8 black chips, poker chips I'm thinking about, 7 red
What is the standard deviation about this?
chips, and 5 green chips. Pick 2 chips without replacement. Let's probably get a red and then black. Let's probably get a 2 greens.
Seven. Seven. Black. Greens. Green.
Oh, that's probably. It's almost. So how's this work here? It's probably that first guy is red.
7 out of 20.
Beautiful, 7 out of 20. The person, I'll get this sometimes, remember that? Somebody would say they're red when would it be 1 out of 7? What are they thinking?
There are 7 and you pick
There's 7 red, I want to get one of them. But the probabilities are always based on the total chances you have to match something. I should have more than just one chance to match it because there's 7 red chips. I should have 7 chances to match it out of 20 I could possibly get. I'm not going to definitely get a red chip. That's really what that's kind of saying. And just getting my favorite red chip. Right? This would be more like, given that you picked the red chip, what's probably got your favorite one? That would be that guy. So 7/20 and means multiply.
8 of 19.
Yeah.
8 of 19.
8 out of
19.
19, I love it. Because it's without replacement, I lost a chip, bless you. So everybody cool with why that bottom does change, but the top doesn't? Because I didn't lose any black chips.
Not totally.
Totally.
Not totally. I'm not entirely certain why it wouldn't change. Because what if you did grab a black one?
Oh, that's what I'm talking about earlier. This mathematical statement is just talking about the situation where this does happen.
Oh.
So if I didn't get a red chip first, I wouldn't even, like you were saying earlier, you would keep going, but really not. If I want this to happen, theoretically, I wouldn't keep going.
Oh, okay.
So I say 7 out of 20 times, I'll actually say what this first thing says. And then times 8 out of 19 times, I'll get that black second chip. So of course, what about the 13 out of 20 and the 11 out of 19? Do you guys see that? That's the probability of other things happening in each step. That's not included here, is it? So those things could happen. They could be parts of other questions. I'm talking about this question and these things happening. Cool. Everybody understand that question? I get that. It's a really good question. I didn't necessarily get a red first. I didn't, why would, maybe I got a black one. Well, then I wouldn't be in this problem. I wouldn't be in this statement here then. Yeah.
Well, that was my question. Like, what if you did pick a black one first?
What's the chances of that? 8 out of 20, right?
Yeah.
So this is specifically just a 7 out of 20 chance that I do get a red one first. So that's why I can say on the next step that I did get a red chip. Because I've already said there's only a 7 out of 20 chance that I could. Assuming that I did, there's an 8 out of 19 chance that I would then get a black. So it's really an assumption we're making, assuming that I am in this situation. Because nothing's actually happened. I don't have any chips anywhere, do I? Right? And then this is whatever the hell it is.
15%.
About 15%. And what about 2 greens? So the first one's green.
Green is 5.
5 out of 20. And the second one's green.
4 out.
Beautiful. 1 less chip, 1 less green. So the only time they both change is if the first dude and the second dude are in the same situation. In this case, they're both green. Yeah. So this would be 1 out of 19, which is just over 5%.